All right, hello there. So, this is the third and I think final video of section 1.9. And after this section, we will be moving into, I might have said this before, section 2.1. So this video, we're going to take sort of a big turn, almost a turn that a big enough turn in a way that I'm a little surprised your book made this one section. But I guess we're still going to be talking about linear transformation, so it's still very applicable to the sections we've been talking about or the material we've been talking about in 1.8 and 1.9. So I'm just going to jump right in. What I want us to remember throughout this lecture here. So remember this kind of way of thinking of a linear transformation where I'm taking a vector x and Rm, and you can think of t as sort of like mapping x to this vector, this should be Rn to Rm. This is usually the standard way we do it. Rn to Rm. And so remember, for each linear transformation going from Rn to Rm, so for each of these, we've got a matrix, right? So that was sort of the big punchline of the first video of this section and section 1.8 was that every linear transformation is a matrix and every matrix is a linear transformation. And remember, we can always define it like so, right? So secretly what's going on here is matrix multiplication sending x to t of x, where A is an m by n matrix. So m rows, n columns. Keep that in mind. So we want to talk about two sort of distinct properties that a linear transformation can have. And then we want to discuss how we can determine when a linear transformation is going to have those properties based on the matrix A that is associated with it. So I want to just jump right into it. We say that a map T from Rn to Rm is onto if every b, and so here b is a vector, in Rm is the image of at least one vector x in Rn. So what does this mean? All right, so this means that for every vector I can find in my space here, so every vector in Rm, and so think of these points for now as representing vectors, there is at least one arrow pointing into each one of these points. That is, every vector here, there's some vector x such that a times x is equal to vector b here. And so that is that t of x is equal to b. So visually, I want to kind of talk about what onto and what not onto looks like. So this linear transformation I drew here is onto. Because notice, pretend that this space only had 3 points in it. Each one of these points has at least one arrow going in. And in fact, just to specify, each point could potentially have more than one. The qualification we want is that each point just has at least one. Right, so notice here, we're not too concerned with the fact that this point has 2 arrows going in, just as long as each point has at least one arrow. So this would be onto. Now visually, what would not onto look like? Not onto would look like that. So notice that here, this point doesn't have any arrows pointing into it. That is, there is no vector x such that t of x is equal to that vector b. And so this is not onto. All right, so we want to know, when is a linear transformation onto? Well, so remember that a linear transformation is just a matrix. So what does that mean? Well, by definition of onto, if t of x is equal to b for every single vector b, right? So if for every single vector b, I can find a vector x so that t of x is equal to b, well, remember, t of x is equal to a times x, right? So this implies if t is onto, then the matrix equation ax equals b has a solution for each vector b in Rn M. So all that this is saying, all that onto is saying, is sort of just the linear transformation definition of saying that this has a solution for each b in Rm. So here onto is equivalent to saying this. And so if you remember in section 1.4, we went over this theorem of all of these equivalent sort of definitions or way of looking at a matrix. And so, again, we actually know how to check if ax equals b has a solution for every b in Rm. So notice that this happens, that ax equals b has a solution for each b in Rm if, so we'll say, and I'll put this as a separate bullet point, ax equals b always has a solution if the row-reduced echelon form of A has a pivot in each row. So I'll sort of circle this bullet point here because this is very important. This fact right here tells us how we can determine if a linear transformation is onto. Because every linear transformation has an associated matrix. Work your way down the board here. If that associated matrix can be row reduced and has a pivot in each row, well, then that matrix has a solution for each b, or the matrix equation, excuse me, has a solution for each b, and that means that the transformation is onto. So we're still introducing all these new definitions, and ultimately, like, how do we, answer questions? Oh, we just row reduce and look at the matrix. So we'll go over some examples of, how to actually sort of apply this to real matrices, but this is how we determine if a linear transformation, for the moment, is onto. That if we can row reduce the matrix and it has a pivot in each row, that is, when we look at the RREF, there's a leading one in every single row. That means the linear transformation is onto. All right, so that is onto. Now let's move on to the next new definition. Now I'll just erase both of these. All right, so we say that a matrix transformation is 1 to 1. So a map, or sorry, not matrix transformation, a linear transformation. Is 1 to 1 if for each vector b in Rm, so again, we're still looking at what's going on in the codomain here. That vector is the image of at most one vector in the domain. So notice the difference here. 1 to 1 is saying that each vector is the image of at least one. Or sorry, onto. Forget that. Onto is saying that each vector is the image of at least one. 1 to 1 is saying that each vector is the image of at most one. So what does this look like pictorially? So this linear transformation is 1 to 1. But notice it's not onto. So here, notice each dot only has one arrow pointing in. And so since each dot in the domain has at most one arrow pointing in, it's 1 to 1. And so you can think of this actually sort of as the vertical line test of matrix or linear transformations, right? That like each element in the range should be mapped to by most one element in the domain. And so the fact that this point doesn't even have a map is okay, right? Or it doesn't even have an arrow is fine. It's 1 to 1, but not onto. But something like this would not be 1 to 1. Because specifically, notice here, this point has two elements mapping to it. Two arrows going into that. So much like we did with onto, I want to come up with some sort of way of determining by looking at a matrix, and specifically probably row reducing the matrix, to be able to determine if a linear transformation is 1 to 1. So what qualities about a linear transformation can we look for to determine if this is true? Well, so what should happen is that for each vector x, right, I shouldn't be able to find more than one vector x such that ax equals b has a solution, right? So if there's, right, remember ax equals b, that matrix equation has either 0 solutions, one solution, or infinitely many. It should never have infinitely many, right? Because that would mean it's not 1 to 1. So let me state this. This is going to be sort of an interesting theorem and proof because I think this is one of the first conditions that we'll state that's very much, I look at it and it's like, well, it's sort of interesting. Well, you'll see. I guess it's one of the more, what I was trying to say, it's one of the more unexpected sort of things that we'll have seen so far. And it'll be one of the more involved proofs, actually, that we've seen so far, too. So this pops up as Theorem 11 in your book. So we're going to assume that T maps R into Rm. As we have it up there, A is going to be the matrix corresponding to T. Then T is 1-to-1 if and only if the equation Tx equals 0. And so what this is saying is, we're going to look for a vector x which maps to the 0 vector, has only the trivial solution. So what this is saying is that this transformation is 1-to-1 if and only if this has only the trivial solution. So why would that be enough to make this 1-to-1? So notice if and only if statements mean that each sort of side of this logical statement implies the other. So what this is saying is that if I have a matrix transformation that's 1-to-1, then I know that the only vector which maps to 0 is the 0 vector. That part of it we know because, remember, for every linear transformation T, the 0 vector has to map to the 0 vector. This was a fact we proved, I believe, in section 1.8. And so because of this, right, if T is 1-to-1, well, that means that at most one vector in Rn maps to any specific vector in Rm, right? So if we look at an example of our 1-to-1 mapping, right, each vector on the left, or each vector on the right, has at most one vector on the left mapping to it. And since we know that 0 always maps to 0, if T is 1-to-1, then there can be nothing else that maps to 0. So T is 1-to-1 very quickly implies that Tx equals 0 has only the trivial solution, just sort of by what we already know. But what about the other direction? So certainly if we know that Tx equals 0 has only the trivial solution, we know that certainly 0 doesn't have more than one arrow going into it, right, on this side. But why does that necessarily imply that no other vectors have arrows going into them? So the way we're going to prove this is sort of by contradiction. What we're going to do is we're going to assume that there is some other vector that has two arrows mapping into it, and show that that gives us a solution to this that is non-trivial. So assume that for some b in Rn, we have one vector x1 and one vector x2 that both map to b, right? So this assumption is assuming that the linear transformation is not 1-to-1. And that, of course, x1 and x2 are not equal. All right. So our goal is to try and show that there's a non-trivial vector which maps to the 0 vector, because that will prove this statement. So notice, well, I'm going to write this sort of in another direction. Because T of x1 and x2 are equal, right, the 0 vector is equal to their difference. But notice T is a linear transformation. So what do linear transformations allow me to do? They allow me to combine these two expressions into one, right? So that means that T of x1 minus x2 is equal to the 0 vector. But what did we initially assume? x1 is not equal to x2. So that means I just found a non-zero vector that maps to the 0 vector, meaning this has a non-trivial solution. So, theorem 11 is true. That we know that a linear transformation is 1-to-1 if and only if this has only the trivial solution. All right, so moving out of the proof, how does this apply to us in terms of matrices? I'm going to leave this theorem on the board and sort of talk about what we can deduce about the reduced row echelon form of a matrix now. So, if this is true, right? So this last line here implies that the matrix equation AX equals 0 has only the trivial solution. And now, if you'll remember, this means the columns of A are linearly independent. But that doesn't tell us a whole lot about the reduced row echelon form yet, or does it? Well, this means that there are no free variables in the RREF of A. So how do we tell if a linear transformation is 1-to-1? We look at the associated matrix, we row reduce it, and ask, do we see a free variable? If we see a free variable, then it is not 1-to-1. If we don't see any free variables, then it is 1-to-1. And so that should sort of make a little bit of sense, right? Like intuitively to me that makes sense, because remember, free variables were the things that potentially gave us infinitely many solutions to a specific matrix equation AX equals B, right? And so if AX equals B, or if the row reduced echelon form of A has no free variables, remember that means we row reduce and we always get that scenario where all of the variables get immediately fixed. And so that means that each matrix equation AX equals B has exactly one solution, which is exactly what 1-to-1 means when we're talking about matrices as linear transformations. So I want to end, I'm going to draw 4 matrices on the board. And then what I will do is I encourage you to pause. All of these matrices are going to be row-reduced echelon form matrices. I want you to use the characterization of onto and 1-to-1 to determine if this matrix represents an onto or a 1-to-1 linear transformation. So I'll say that in general to do this, and I'll probably put up an example where we row reduce, it's just the video is getting a little long at this point. In general, if you're given a transformation and you're given the matrix for the transformation, so example, determine if each RREF matrix represents an onto / 1-to-1 linear transformation. And so in general, if you're given a transformation and given the matrix, you'll have to row reduce and look at the row reduced echelon form. But I want to look at a bunch so we can kind of start to see what the different types of matrices look like. And row reducing 4 matrices would take entirely too long. And so as I'm writing these out, start to think about what each one represents, using, again, those characterizations of 1-to-1 and onto. All right, so each of these is an RREF matrix, and determine if each one represents onto or one-to-one. All right, so remember onto is that we have a pivot position in each row. One-to-one, we should have no free variables. So this first matrix has no pivot position in row 3 and no free and a free variable in x3. So this is neither. Next, this matrix has a pivot position in each row, no free variables, and so this is both one-to-one and onto. This reduced row echelon form matrix, well, it has a pivot in each row, but notice it does have a free variable in x4, right? And so this would just be onto. So notice in specific too, you don't always need a 0 row, right, to have a free variable. So here, x1, x2, x3, x4. x4 doesn't correspond to a pivot, so it's free. So this would just be onto. Finally, while there is not a pivot in each row, right, there are 2 rows without pivots. There are only 2 variables, x1 and x2, and neither is a free variable. So this would just be a one-to-one matrix. So examples sort of each type of case you could get. Sorry about the video running a little long, but I wanted to make sure I got everything in.